Okay, so this might be one of my favorite topics in the world of physics, specifically mechanics. Um, Inclined planes. They're hills, people. They're just slopes, but I love this idea. Okay, when we have something like a hill, a ramp, a slide, an inclined plane, we need to continue to think about things for Newton's laws, F equals ma, but we need to put a slight twist on the problem here. And the reason why is this. Uh, Whenever we put an object on an inclined plane, a ramp like this, the weight of that object is still going to act directly downward. Gravity is always, 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 always pulling us in towards the center of the earth, which is down no matter where you're standing. Okay, so our weight here is down, and remember that weight is mg. Now, because our weight is pulling us down, we actually have to break that weight vector up into its component parts. And you're like, wait a second, time out. In the prior problems we did, we had a nice axis like this. We would draw our object and the weight vector is on the axis. Like we could go back into some old things we did, like this equilibrium problem with the monkey. And look, the weight is on the axis there. What do you mean we have to break it up? Well, what we're going to be doing on inclined planes is we're going to be rotating our axis. Notice here, these dotted lines, this is our new axis running up and down and left and right. Our axis is now turned into along the plane, so down the plane or up the plane, and then away from the plane or into the plane. Okay, so we've kind of rotated our axis here, which is a kind of weird thing to do, but there's a really, really brilliant reason why we do this. And why we do this is as follows. So let's just take for a second. We have, whoa, what is that? That is a weird, weird thing. Let's just take this shape. Okay, let's take a shape like this. It's like a little L. If I take a look at this L here, and I notice that the bottom of it is just left and right, and the top of it is up and down. If I take this L, I can rotate it. And if I rotate it to the right 90 degrees, I now get this shape. Okay, it's just been rotated. That's all that's happened here. Well, why is this so important? Well, if we had a box or a person or whatever, they need to have a force going down the plane in order to get pulled down here, okay? And if, let's say it's you ever been on a slide at a playground before, and all of a sudden it I don't know, you go down it and you get like a brush burn from it. Your arm gets caught on the plastic or the metal or something. That means there's some friction opposing you going up the slide. And furthermore, if you're sitting on the slide here, this is a surface, you have a normal force pointing away from the surface of that slide because it has to be perpendicular to the surface. It is normal to that surface there. So if we look at all three of these arrows here, they're either down the slope, up the slope, or perpendicular to it. The only thing that is not in the directions of the black lines here is the weight. The weight is the annoying piece here. So what we've done is we've shifted our axis. We've kind of tilted our head here to change what up and down actually are and what left and right actually are. And because of doing that, we need to break up our weight vector into its component parts. And the way we can do this is actually pretty straightforward. If we take just a look at the weight vector, we're going to use a little bit of geometry to show us how to do this. So, whoops, let's undo some of that. So if we have, in this example down below, we tilted this up 45 degrees. So we moved up this way 45 degrees. Well, when we did that, what that actually also said was, since this, L shape was connected, is we tilted this over 45 degrees. And what that means is if we kind of make an axis up here like this and like this, if we backtrack this black line here through then this angle here, which was 45, must be the same as the angle down here. There's some geometric property here. They're like interior angles or blah, 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 whatever it is, right? Like those are angles in such a way that both of them will be 45 degrees. So if we take a look at our inclined plane here, this angle theta is the same angles down here. Whatever it is, we've tipped everything the same way. And what this causes is this allows us to say that, look, if this is our weight, then this vector right here, this component of the weight, or the weight vector acting perpendicular to the slope, and the weight vector acting down the slope, or the parallel component of it, those are across from this angle here. And what that allows us to state that this is the opposite side, this is the adjacent side, and this is the hypotenuse. Wipe. It kind of looks weird, but if you kind of like really tilt your head around, you're like, yeah, that makes sense. That's a pretty standard triangle. So in doing this, if we did a little SOHCAHTOA here, we would see that the weight component, or the component of the weight force acting down the plane here, that parallel component, that is equal to the weight times the sine of theta. Or we could write that as mg, because mg is the weight, multiplied by the sine of theta. And we see that the amount going perpendicular or into the actual surface, whatever it is, a slide, an asphalt hill, whatever, that'll be equal to the weight, which is mg, multiplied by the cosine of theta. And the way that I like to remember this goes back to that wonderful F equals ma song that myself and my four identical brothers made, where it goes, sine of theta acts down the plane, because sine of theta acts down the plane. So that's what we're going to be looking at here. But from that, it is still just an F equals ma problem, where we are setting either up or down the plane, like positive and negative, and away from the plane or into the plane as positive or negative. So it's still F equals ma. We've just twisted our axis, and because of that, kind of shifted how some things work out. Now, due to this shift, there are a few other things that pop up a little strange. Normally, when we've been doing problems, we say that, hey, look, if you have a weight, then you have a normal force, and your normal force is just equal to your weight. And we saw yesterday, in prior days when we looked at like the toboggan problems, where if things are acting at angles, maybe the normal will not be equal to the weight, and this is one of those cases there. The normal force is actually going to be balanced or equal to the perpendicular component of the weight. So it's going to equal the perpendicular component there. It's going to be equal to the mg cosine of theta term. And that kind of makes sense, because imagine if you had a really steep slope, like up and down. You know, if your slope's directly up and down and you put an object here, it's just going to fall. There is no normal force then, right? Nothing's pushing back on the surface. So we see that there. Furthermore, if we have something like friction, we need to make sure that we're doing positive and negatives, adding or subtracting from the parallel component of the weight, so the mg sine theta. And we'll see that in our example that we're looking at. The real key here is that we have tilt the axis. Okay, we've tilted our axis here, we've rotated it, and we've reassigned it. So let's see what this would look like in a problem. If we go down here, we have a child. Well, maybe we don't, but there is a child going down a playground slide. Maybe this is you at one point. I know where I live, there was this giant metal playground slide. It went and went and went. It was huge. It would get really hot during the summer, but my dad one day, he took a power buffer out to it, and he waxed the whole thing. And then we sat on butcher paper, and we literally like flew down it. It was very, very dangerous, but it was very, very fun. But we have this child, and they're going down a playground slide, and we know that it's inclined at an angle of 28 degrees below the horizontal. We're looking for the acceleration of the child. So this is what we're looking for. That's our green light. And what we know is that the kinetic coefficient of friction between the child and the slide is 0.415. So let's draw a picture and then a free body diagram, and then start working our F equals MAs, just like always. So if here is the slide, well, here's the horizontal. it said that the slide is like this, where it's 28 degrees below the horizontal, like that. But this is actually fine. If we think about, the ground that the slide hits at the end here, this 28, we can do the same like opposite interior, blah, blah, blah geometry thing that I can't remember the words of. This is a physics class, people. We just know how things work. We're not certain the rules of them. But these angles will be the same. Okay, so we don't really have to worry about the horizontal up here. We can just say, there's the ground, 28 degrees. Here's a nice slide. And if we put our child on the slide, there are some forces acting on them. There is a weight pulling them down. The weight pulls down on a free body diagram. There's the normal force, which is going perpendicular to the surface. And then because the child is moving down the slide, friction has to oppose that. So there's some friction acting back up the slide. And we know friction is fun. Okay. If you're looking at this free body diagram and you're like, Mr. Botzer, why didn't you draw the mg sine theta term here? Well, you don't draw that on a free body diagram. That is a component of the force. Free body diagrams only take the forces. The components of the forces we have to draw off to the side. So if we break up this weight vector off to the side, here is that mg cosine of theta term for the weight perpendicular, which is going to equal the normal. And here is that weight parallel term, which is the mg sine of theta. Okay? So if we were drawing components, we would have acting down the plane. There's your weight parallel. Here is your weight perpendicular. There's the normal. And here is friction. And as classic physics is, we need to choose positive and negative directions for everything. So let's just choose the direction of motion to be positive. So if the child is sliding down the slide, down will be positive, up is negative. And for the normal and the weight, the perpendicular component of it, doesn't really matter what we choose. They're going to be equal. So we'll just call that positive and this negative. So if we go in, we start applying our classic F equals ma strategies here for both our left, right, or up, down the plane, and our away from the plane into the plane, we can set this up. Because we're looking for the acceleration, our F equals ma equation won't be equal to 0 because we're actually looking for the acceleration here, right? We're looking for that value. So if we set this up for the up and down, or going along the slide, we've got two forces there. So we better have two forces on the left side of our equation. We've got the weight parallel, which is mg sine theta. So mg is actually given to us in the problem. It's 343, guilty spark for you Master Chief fans out there. So our weight here is 343 times the sine of theta, 28 degrees. And that will be minus the force of friction. We know friction is fun, so that's going to be mu times n. And we actually know the value of mu. It's 0.415, so 0.415. So this is mu and then n. We don't know the normal just yet. We're gonna have to grab it right here. So that normal is actually going to be the mg cosine theta term. So I guess we could just put that in there instead. That entire normal is going to be 343 times the cosine of 28 degrees. A lot of parentheses. And this is going to equal to ma, which the mass of our child was 35 kilograms. And the acceleration is actually what we're looking for. So that is our F equals ma equation. It's still classic F equals ma. Nothing has changed there, but we had to do a little bit of work ahead of time to kind of tilt our axis, find the broken up components of the weight vector, sine of theta acting down the page, cosine of theta acting in and out of the page, and then now we can solve this. Looking at this here, this is actually totally solvable. It's not too crazy. There's just some math we have to do, and it's best to take it a step at a time. But notice that everything here is all numbers except our variable we're looking for a. And since it's the only unknown on one equation, we can solve for it. So let's just break this down bit by bit so we don't flub anything up as we're going along. I'll try to draw arrows showing what we're doing each step. So first, I'm going to put the 343 cosine of 28 together. So 343 times the cosine of 28. Make sure your calculator is in degrees. I get 302.85. And then if we put the rest of this back, 0.415. So now I'm going to multiply this by 0.415. And this together is going to give me 125.68 newtons. On the left here, and technically there's a negative. On the left here, I've got 343 times the sine of 28 degrees. So 343 sine of 28. I get 161. So 161.03. 161.03 as I'm carrying it down. And this will still equal 35 kilograms times A. This is a Newton as well. Now, to go and solve this, I just need to subtract the 161 and the 125, and then I can do a little bit of division there. So let's subtract the 161 and 125. 161.03 minus 125.68 gives me 35.35 newtons, and that's going to equal 35 kilograms multiplied by an acceleration. And at this point, we just divide by the 35, divide by the 35. That's a lot of 35s. And what we'll get here is our final answer is that our acceleration will be 1.01 meters per second squared, because that's our units of acceleration. So once we got that F equals ma equation set up, it was just some math to kind of churn it out. But the actual diagram itself was given to us by the sine of theta and the cosine of theta there. Okay, so with that, this is kind of the first example we've done here, and it is finished for both that and our notes. In our next example, we'll be looking at what happens when we pull someone up a hill on this incline as well. But until then, adios and take it easy.